Hey, welcome to IoT 205. We're going to talk about secure best practices, especially with Google Cloud, and how do you incorporate that in IoT. So let's start. My name is Pushkar Sharma. I'm a product manager in Google Cloud in IoT, and with me is Nicola Scieli. He'll be joining me and talk about secure elements and IoT security. He's the senior marketing manager and application manager at Microchip in the secure products group. So let's get started. So I'll set up the agenda here, and then Nicola will take over. So first of all, we'll talk about IoT device root of trust. What does it mean, and why it's important? Then we'll talk about some crypto algorithms and what different algorithms are and how do you think about those. Then there are different methodologies. There is the hardware root of trust, there is a software root of trust, and then how do you think about which one is better or not. Then there are different implementations too. Even if you think about hardware, there are different ways you can make things better and also the way it gets compromised. And you want to think about all those aspects when you choose your hardware root of trust. And then the second aspect will turn into like, how do you put that in real life? How do you provision them at scale, and how do you operationalize them? And we'll do a demonstration of all the aspects of security, whether it's a firmware validation, onboarding of the IoT in IoT platform in Cloud IoT. How do you do that with secure elements? So with that, I'll hand it back over to Nikolai, and then he'll talk about those.
Thank you,
Thank
Pushka. So basically, when we're designing an IoT product, as mentioned, one thing to start with is, well, first we need to basically understand a little bit what we are facing in the market. There are a number of attacks that have been widespread over the past few years, and the frequency of attacks is really increasing. That's really one of the important points. The frequency of attacks is increasing rapidly, and you see also the scale of the attacks is increasing, which, I mean, some of the attacks are essentially pointing to pretty much every single connected device. Now, with that in mind, when you're designing a product for a connected product, you will need to basically build that with a root of trust. So many people are using the concept of root of trust. So what does that mean for an IoT device? So for an IoT device, root of trust typically we believe means two things. You need to basically make sure that the device runs genuine code, so code that is supposed to be running, and also the device is connecting to the service it's supposed to be connecting to. So really, before connecting to any remote service, you need to make sure that the device runs the code it's supposed to be running. And only the combination of those two attributes make the device secure. And basically, that's what we call the root of trust for a connected device. So in order to be able to connect a device to a remote service, you need to have a trustable identity. So what is a trustable identity in our world? So in a digital world, a trustable identity is a number. It's nothing more than just a number that basically you can make a copy of that number. That copy will be a perfect copy. You will even know that someone has made a copy of your private key. So a trustable, verifiable, and unique identity is essentially a private key that is very easy to copy, which means if I have a copy of your private key, I have essentially all the accesses that you have. So preventing someone from making a copy of that private key is essential. Right. So it's all about protecting the key. Basically, if you're looking at that number, that is the private key, there are a number of principles to apply to protect those numbers or those keys. One is the Kirchhoff's principle, which basically says that in the system, in a cryptographic system, everything should be known, and except the key. So what you should really spend your time on protecting is the key. So the key is the secret. Everything else should be known. And Claude Shannon actually also stated essentially the same thing, that basically you should assume that the enemy, the attacker, knows the system. So closing the system down to making the system a secret is not going to make the whole system secure. Now, there are some examples where those principles have not been implemented. So if you're looking at back in time where the phones were basically using the GSM specification for connecting, for delivering text messages or connecting to their networks, basically the security scheme of GSM was based on a secret protocol. So the protocol was secret up until the time it was not secret anymore. Right? So at that time, basically, it was possible to spoof GSM messages and send text messages, spams to the network. So basically, again, security of a system should only rely on the secrecy of the key itself. If you rely on anything else, it's likely that you're going to get hacked. Right. The next thing to consider is you should only use industry standard algorithms. So these algorithms are the major benefits are the fact that these algorithms are widely studied. They've been vetted by regulation bodies that we can choose to trust. And basically, they are coming with a set of documentation that tell you on how to use those algorithms, because many of the cryptographic algorithms, if they're not used as defined, they are potentially exposing weaknesses. Right. And also, some of the main benefits are the fact that then you can get interoperable systems. Now, when it comes to how to implement that root of trust, so you have that connected device that basically runs software for your connected thermostat or whatever gadget connects to the cloud. Now, you have all that computing power that is in that device. So why not using that computing power to run those cryptographic algorithms? Now, the thing is, if you run cryptographic algorithms directly on software in your computing engine in a device, what that means is the keys that are used by those cryptographic algorithms are also there with the code of the algorithms. So if the keys are there, and we basically mentioned that the keys are the things that need to remain secret, then we need to make sure that nothing in the system can leak out those keys. And Heartbleed, that has been documented by Google back in 2014, is an open SSL bug that basically was allowing hackers to go and have direct access to the memory of the OpenSSL server. What is important to mention in that case is 2014 is when it got published as a valid attack that was demonstrated. Now, the thing is, the bug got introduced years before. So it's likely that someone has been able to exploit that way before it got documented and patched. Right, so basically the question is, if you go down that path of software implementation of a cryptographic algorithm, how many bugs do you have? Right, so everyone knows that perfect software is not possible. So if you want to have a secure system based on software implementation, that means that you have to have essentially perfect software. So that's something that is an elusive goal. So in that context, very often the systems that have been architected for connecting devices securely to a remote service have been architected around secure elements. Secure elements are dedicated pieces of hardware that basically are designed for storing cryptographic keys and using those cryptographic keys in a safe way. Now, the thing is, if you're looking at your system now, you're ending up with essentially a duplication of resources, right? You have your main computing engine, the microcontroller in your thermostat, for instance, that will have a computing core, will have memory, will have code, will have power and clock sources. Now, your secure element will have all those blocks as well. So naturally, the next question is, why don't we combine that? Why don't we have hardware products that basically combine all those features in one single piece of silicon? Because then we are duplicating a lot of resources. We could really find ways to optimize that. Now, if we do that, so many systems have been doing that, naturally. So if you share, for instance, the core. So sharing the core in such system is, you can think about this as a processor that would be able to run code with multiple levels of privilege. That's essentially what runs in any modern operating system today, Linux, Windows, all those operating systems use that concept where you have a kernel code that is privileged, that has the right to access everything, and user-space code that has very limited access to the component of the system. So now, naturally, you would put your cryptographic keys, your secrets, in the most privileged place where basically the user code would not have access to. So now this isolation is typically enforced by the hardware itself. So the processor would have capabilities of making sure that memory that is supposed to be accessible by the kernel is not accessible by the user space. Right. Now, there are attacks, like, for instance, Meltdown Inspector that have been mounted by teams back quite recently in 2018 that did impact pretty much all PCs in the market. And that was mounted by Google Zero Project, Cyber Technologies, and the Graz University in Austria. And what they've been able to do is they've been able to leverage hardware optimizations of the processors, where basically all those high-end processors, they use speculative execution, right? So what they do is since memory access is so expensive because it stalls the pipelines of the processor for a very long time until the data or the code get into the processor, then basically what they do is those processors execute all the code they can, speculating that all the code has to be executed, and then once they know which code is useful, they trash out what is not useful. But the side effect of that speculative execution is the fact that you can essentially, all that code gets into cache. So in the cache of the processor, you have all that code and memory, data memory, basic, and all the secrets of your crypto algorithms end up being there. And they've been able to mount an attack that was able to feed those data out of the cache into the user space. So basically, what is really important with this attack is the assumptions they had. They assumed that basically they had no physical access to the system. So this is something that you can do entirely remotely. And they were assuming that they had no weakness in the operating system, so there's no bug to leverage. And there's no software vulnerability in the system to exploit either. So they were essentially assuming that the system was perfect, they had no physical access to it, and they were still able to mount, to gain access to privileged memory, and basically get access to the secrets that were in that privileged memory. So again, this sharing the core in that case was quite harmful, even though there was hardware isolation, hardware-enforced isolation between the different pieces of code. Right. So looking at sharing the cloak source, so that's another piece of the system where you may want to share your power management or your cloak source. So basically, this is an attack that is quite fascinating. So CUKSCREW, that was mounted by the Columbia University back in 2017, is basically leveraging the fact that pretty much all modern high-end processors have power management features that allow them to scale frequency and voltage as needed. So if you need to perform a very demanding task, you will be increasing the power to the processor. You will be increasing the clock frequency to have it clock faster. And when you want to save power because you're not doing much, you will essentially be scaling them down. So we'll have lower voltage, lower frequency. And when you're doing this, you may end up violating some of the hardware timings of the past. So if you look at the picture, this is a picture of a number of flip-flops. So these are the gates you have in a processor. And these need to be clocked at a certain frequency. If you're violating the frequency of those flip-flops, you will essentially introduce a fault into the chain. Now, what they've been able to do is to basically build a remote fault attack. So they were able, by just scaling the frequency of the clock, to inject a fault into the hardware that was then starting to misbehave to the point where basically it was leaking out, it was giving privileged access to the memory. So you could actually mount a remote fault attack without having any physical access to the device, just by using user space code, and then essentially injecting faults in the code that gives you privileged access to the memory. right? So now, in that case, you get access to the trusted memory with unprivileged code, even though you have all those hardware boundaries that prevent, in theory, to have access to that memory. You remotely still access that memory, right? Now, the last piece is how do you, if you share the memory, what does it mean for your system? If you're sharing the memory, for instance, in those systems is a DRAM. So DRAM cells are quite packed together in the silicon. So silicon space is cost for a processor, right? So you want to have them as close as possible. When you get them very close, what happens is they will be coupled capacitively, right? So when you're changing the value of one cell, you may influence the cell that is the neighbor. So there is a demonstration based on what is called Rowhammer. That's another Google Zero project that was released in 2015, where they've been able to execute code that was successfully being able to so use a space code, not privileged code, that was able to change the memory footprint in some rows of the memory that were influencing the neighboring cells enough for those cells to basically flip the bit for privileged code. Now, suddenly, your privileged memory is not privileged anymore. You have access to it because you just flipped that bit by just changing user space code. So it's quite fascinating. So again, it's using the fact that those memories are shared and then packed together, basically. Now, conclusion is actually sharing resources in a secure system is quite a complex task, right? So then you need to think about how you can defend yourself against all those type of attacks that are quite clever. But all those attacks have one thing in common. They have access, so this one system where all those resources are together. And basically, all those attacks are leveraging the fact that there is a weakness in the implementation. It's a hardware weakness, that's very clear. But it's a weakness based on the fact that those resources are shared. So basically, the point is, if you want to make sure that none of those attacks are possible at all, you want to have a perfect isolation. So you don't want to actually combine those resources. You want to keep them separate. If you keep them separate, there's no way of mounting any of those attacks, right? And this is what secure elements basically do, right? Secure elements basically keep all those resources completely separate. They have dedicated computing core for handling cryptographic functions. They have dedicated memories for storing the keys and the secrets, and they have dedicated power and clock sources that you cannot manipulate from the outside. So for instance, so that's why we basically suggest that for best-in-class security implementations, you should be using a product that is specifically designed for security in mind, right? So basically, secure elements are devices that are not designed for power consumption optimization or computing power optimization like those processors that I talked about, but they are designed really for security as number one goal. So those devices have many different type of defenses to basically be able to defend against any known attack. So that's really what they're designed for. So those devices have typically active shield on the top. So you can see that on that picture where basically there's no physical access to the device itself. If you were to get access to the device physically, you would not be able to get to the circuits. So those circuits are active shields where you basically, it prevents access to the underneath logic. Memories are encrypted. They are features like randomized math operations, which means that every single operation, regardless of the data you manipulate, will always take the same amount of time because you don't want to leak out any information by just executing the command. Right? If you're manipulating a certain key, you don't want the duration of that manipulation to be dependent on the key itself, or you would be leaking out information about the key. There's obviously no external clock inputs, so the clock is generated internally, and there's no JTAG, obviously. So these are really devices that are designed for security, with security in mind as the first goal. Now, how does that play with the cloud? So Pushkar will talk to you about the security side of the cloud and how those security elements can be used in that context.
Thank you, Nicola. So when we think about IoT in Google Cloud, we think end-to-end, because ultimately what matters to you is the business goal, which is on the right-hand side of this picture. Basically, it's an application you're trying to enable, and what you have on the left, on the extreme left side of these are the assets that you care about. So these are devices, these are factories, these are vehicles you're tracking. There is a telemetry which they are producing, and you want to make sure that gets to the final goal, and you can make sense of it. So we have a lot of products along the way in that journey of the data, which basically would help you to process the data and so on and so forth, right? So starting off from the left-hand side, obviously you will have a gateway. Gateway is a device with a wireless connectivity to the cloud over WAN. And what the primary goal is to secure that connectivity, because these are the devices out in the wild. You want to make sure they're secure. So we talked about secure elements. That would be one thing, and we'll talk a lot more. How can you use the best security practices? And that has been our number one goal when we designed the front end for that, which is the Cloud IoT Core. So that's the product which with my team, this is the goal of the product, is to enable this planet scale connectivity of devices securely at scale, so that you don't have to worry about security at all. And then the data goes into PubSub, and from there on, what you're really looking to do is sort of ETLs and processing of the data. So we have different products, data flow, data prep. You can do cloud functions for rules. So if you want to trigger off certain rules based on the different events, you can do that. And you can store that into different kind of databases, whether it's a time series database or it's a, SQL database. Depending on the type of database, there are multiple choices. But ultimately, what you're trying to do, either you can display real time what's going on, or as you can start to use AI and machine learning, you want to start to predict. For example, let's say in a factory environment, if you have a machine and it's producing a whole bunch of data, but you want to actually create a predictive model of what a failure would look like and when would it happen and what would be the factors for those failures. That's where you would start using AI and machine learning, create a model, train that model using your past data, and then you use the current data to inference what the probability looks like, and what are the factors which could be affecting the failure, for example. And clearly we have Firebase and Data Studio for visualization and application development. So we have end-to-end suite for you from an entire IoT application development. So let's talk about IoT Core. So IoT Core essentially has two parts. One is the protocol bridge. It supports HTTP and MQTT protocols. And so that basically means that all your devices can now connect over these protocols and publish data. And it uses TLS. We'll talk about authentication in a minute. But it is essentially a planet scale ingestion. And the reason we're calling it planet scale, because it uses a Google front end. And this is a front end for all the Google applications, right? Whether it's a Gmail, YouTube, they all use the same Google front end. That means when the device wakes up and tries to connect, it goes as fast as possible to the Google infrastructure. And then you do not have to specify different hubs in different regions. It's a single endpoint it needs to add to. That means that you don't have to, at the manufacturing, you don't have to worry about what endpoints these devices may end up going. It's a single endpoint. And that's the Google front end. And the second part is the load balancing. If you are, let's say, running your own MQTT application like Mosquito, for example, you have to manage that as a VM. It needs to scale up and down as you adding more and more devices. You need to manage those. I mean, these VMs or even containers would crash, right? So what we have in the IoT Core, we just manage it for you. You simply pay by the usage. You don't worry about number of devices, for example, right? So that's something is automatically taken care of for you. The second aspect is the device manager, and this is where the repository of devices. So basically, here you would define the devices, give it a name, give it metadata, and however you want to define your devices, and then would be a public key, and we'll talk about why that's important to establish the connection to the private key, which Nicola just talked about. And this allows you to have a lot of, and it's a bi-directional, second of all. I mean, it's not just one directional. I mean, you can send commands back to the devices. You can do a configuration updates. You can do OTAs through that configuration updates. And then it also allows you fine-grained access through our IAM. So there, you can create your own roles and granular permissions based on the different resources type on it. So essentially, you're grouping these devices into different regions and different registries, and then you can provide different level of access. And there are a lot of logging and API and console access for you to do the full application development as well. So let's talk about authentication, right? So what we are using is standard TLS. There is no difference. Is TLS HTTPS or MQTT, but still TLS. And what here the difference here is actually pretty innovative feature from Google, and that we are using JWT, which are JSON Web Tokens. So we're using these tokens as opposed to using certificate. That means that you do not have to store the certificates on the device. And that basically frees up a lot of memory from a constrained device perspective, and you don't have to go work with get certificates for each devices and have that additional infrastructure. What you simply do is create a JOT, you sign it with the private key, which is in the device itself, and use that in the password field, and you establish the TLS connection. And once the connection is established, then you can send the data. So you do not need to do a full mutual TLS. And we support both ECC and RSA type of keys. So that's the connection, but then you have to think about how the onboarding works. Like, how would I just make it not just one device, but how do I do it for multiple devices in factory? And there are pros and cons, and I'll talk about it. So typically what would happen is that you would have to, for the device to connect, the bottom path here, for it to connect, it needs to know its device ID. It needs to sign a JOT and send that over in that connection. And it needs to know where it needs to go. I mean, it needs to know what registry, what path, what project on the cloud. And then the question is, how does the device get to know that, right? And that's where the provisioning aspect comes in. You have to create that, as a provisioner, you have to create the public-private key pairs and embed that into the device, and create that device ID and put that in the device, and also make sure the same device ID and a public key is on the cloud as well, and in the right project. So this is sort of two-step process you have to do, and this is where the complexity lies, where first of all, there's one problem is, how do you ensure these private keys are actually secure? Because you're actually working with a manufacturer that potentially most likely is a third-party manufacturer, and how do you make sure these keys are not compromised? So you end up spending a lot of effort and money on overhead and high security manufacturing practices, which is expensive. So that's one aspect, and we'll talk about how we can solve that. And the second aspect is, how do you do at scale? Like, how do you get this device ID and public keys and put that into the cloud, in the cloud registry, and how do you register them in the cloud? So we'll try to solve these problems. We'll show you how we're going to do that. So first, we talk about secure elements. So secure elements gives you a good way to solve the first problem, because when the private key never exists outside the device. So these private key pairs are actually, private key and public key, these key pairs are actually generated inside the device. So that means that nobody actually has access to it. You can extract a public key from it, but you will never find out of the private key, right? So that means that you can just buy these secure elements, you can ship it to your manufacturer, and you can ship it on reels like this. And they just take those reels, they populate on the hardware, they ship it, and you do not have to worry about whether this private key has been secure or somebody else has an access to it. So that's a very cool thing. And secondly, the JOT implementation and signing. So it can do that. So for example, with secure element here with microchip, I mean, you can sign that JOT, create a JOT, sign a JOT, and send it. So now it can do that software implementation part for you as well. And it works with our client SDK, which is the SDK we have published. And so you can make it work end to end without much hassle, right? So it's actually very easy to implement, and it's secure at the same time. So that's one aspect. And then the second aspect is how do you do it at scale, right? And even if you use secure elements, you can get blank secure elements where they have not been programmed, right? They have not been pre-provisioned. You get blank program, and then at manufacturing, you can say, hey, I'm going to create my own private key, or and I can inject it. So first of all, you have to have this HSM capability where you would have to work with a third party and create those keys and insert these or put these certificates in it. And the second aspect is that you have to do a careful cloud to registry mapping as well, right? And I think the larger problem is that when you do that, it's the overhead of having these extra steps of programming that may give you customization capabilities, but that is not really, for 90% of the use cases, like you don't really need it. So the second aspect is the pre-provisioned secure elements, which is the microchip has already used a configuration, which is most common, 90% of the time you don't need to change it. And that's a pre-provisioned one, and you can order if the minimum quantity equals 1. So you don't have to order a certain minimum quantities. You get these devices in different packaging options, and then you can simply use them right away. So you don't have to have extra steps of customization or programming of those because they're already pre-programmed. So that actually is very helpful from a supply chain and overhead standpoint. So I will hand it back over to Nicola, and he'll talk about how they are actually also helping with the cloud side provisioning as well.
Thank you, Pushya. So basically, as we mentioned, so the devices, the secure element can be shipped pre-programmed, and volume is down to 1 unit. So that's quite unique in the industry, but obviously volume can go up to whatever you can imagine. We're shipping a lot of those devices every year. So overall, the question is, how do you map those devices that we ship to the individual projects in the cloud? So you need to have a way to extract that public key that will be there to verify the JOT token that the device will sign when connecting to the cloud. And that public key needs to be loaded into the right cloud registry. So basically what we do is when we ship products, we also ship a file that we call the manifest file that contains the public keys of all the devices we shipped. So then you can essentially upload the content of that manifest file into the registry of your choice. And that's what is depicted on that diagram, where basically the provisioner, which in that case is microchip, is the one that is building the device, is getting the script from microchip and then can essentially use those scripts to load the public keys into their registry, right? So basically, as a summary, what we suggest is done when designing an IoT device is to have a hardware root of trust. That's the step number 1, which in that case means you have to have a unique identity and also be able to verify that your code is genuine when you're running it. The second step is really to make sure that you can scale that in volume, and you can use, for instance, in that case, pre-provisioned secure elements. And you also need to use a trusted cloud vendor that has a real end-to-end security approach to those issues. Now, we will try to show you how those type of devices can be used in an easy way. So we have a demonstration here that is obviously with just one device. So we're not trying to demonstrate how the supply chain is easy, but at least at one device, you'll see it's pretty simple. So those devices, basically, we have, if we can show the, so we have basically a microcontroller. We have sensors, so a light sensor, a temperature sensor, and we have on this board a secure element. So that secure element is basically a device that is pre-provisioned that comes directly from microchip. And that board is connected to the network over Ethernet. And basically, the first thing we'll do is to build the firmware. And what we do is typically, as we build the firmware, we also have it signed with a signing private key for the firmware. So if we could switch to the demo. Thank you. So that's Atmet Studio, which is the tool that Microchip is using for developing software for those microcontrollers. And so the project is already basically built for that demo, and then and it's signed. So the firmware is already signed. So then I will then basically program. So give me 1 second. For some reason, it's not powered. Sorry, forgot to power the board. That's going to be better. So basically, what we will program in the device is the signed firmware. So the microcontroller will get programmed with the firmware. So the firmware is actually running the Google C SDK. So that's the library that Google is providing for microcontrollers of that nature. So this is a Cortex M4. And basically, that stack provides you with all the necessary tools you need to connect to the cloud. So once you have done that, so as I mentioned, we need to make sure that the firmware that is running there is genuine. So one way of doing this is to make sure that is to verify the hashing of that firmware at boot up, and basically verify it with the public key of the private key that it was used to sign the firmware. So the private key that was used to sign the firmware is on the laptop. So then I will essentially program that public key, the corresponding public key, to the secure element. So the secure element is basically exactly the way it would come from Microchip, with everything pre-programmed to connect to the cloud, except for the public key for the secure boot. So that secure element, we have a little adapter board that allows you to program over USB the content of the secure element. So I need to switch. One connector that is way too small for my fingers. So sorry about that. Yeah, the switch didn't work. Yeah. Try a third time. Good. So we've been able to, sorry about that, the communication issue. So that was, we have a little switch there that is basically needs to be switched between that connection and the connection on the board. So I'll try to switch it back correctly. And then I connect it to the board when the Google CSDK will be able to leverage that public key when booting. So I can show you basically how we have a debug port on that board that will be displayed on the screen that shows you what the device is doing when it starts. So I'm holding it in reset right now. And basically when it starts validating the firmware. So it did validate the firmware with the public key I just injected in the secure element. And then from there, it basically gets you the device serial number and tells you also the public key that the cloud is getting. Now, I'm not sure the device has Ethernet access right now. We had issues before the section because it doesn't actually get an IP address for some reason. So I'll go through the rest of the demo. So now the next step is to load the device public key into the registry. So if I go to the registry right now, in the Google project, there is no device that is listed. Now, as mentioned, when we ship reels of devices, we also provide a file that contains essentially all the public keys of the of the devices we ship. So you can load those this manifest file directly into the registry. So the script has knowledge of the credentials of the project, everything, and basically we load all those devices into the cloud. So now all the devices that were shipped, that were all part of that manifest file, have been loaded into the cloud. So you see onboarding devices has become very, very simple. It's really about loading a single file, basically. And if the device has internet access, we should be able to get to have it publishing data. So let's... So I don't know if we have Ethernet access right now. Probably not. So yeah, I don't think the device is capable of connecting to the internet right now. So sorry about that. But essentially, that shows you all the steps we have in order to onboard devices. So if you could go back to the presentation. Oh, it's coming up. So sorry, I gave it too fast. So you see there are two sensors. So basically, there's one sensor that is a light sensor. That's the one at the top of the graph. So if you can go back to the graph. So the light sensor is there, and there's a temperature sensor. And if I basically hide the light sensor, the green line will go down. Right. So the data are basically captured in a device. The device is authenticating its own firmware with the CUKSCREW element. Then it's using also the CUKSCREW element pre-provisioned private key to connect to the cloud, and then passes the data to the MQTT broker, pub sub, and then finally gets into database and gets displayed in Grafana. So that's to show you that it's quite simple to using all the tools we provide. So a CUKSCREW element that is pre-provisioned, that can be in very low volume or has high volume as you want. And you can essentially implement all the different steps we talked about today with the Google Cloud and have those devices loaded into the cloud very easily. Right? If you could go back to the main slide. Thanks. So that's basically we're showing all the steps we have in that demo. And as I mentioned, we basically compiled the firmware, loaded the public key into the CUKSCREW element, then we uploaded the manifest file into the Google Cloud repository. And basically, once all of that is done, it could be done at very large scale. It's obviously here just with one device, but it could be with the loading of the public key is not something that you would have to do one by one. We can do this for you in our production line at volume. Loading the manifest file is essentially something that loads all the devices at once. And then finally, once all of that is done, when CUKSCREW element and the Google Cloud CSDK come together, they work together to connect to the cloud very easily. So thanks for your attention. Your feedback is really appreciated. So if you could provide feedback as explained on that slide, that would be very helpful for future sessions. Thank you.